Okay, there are literally thousands of feedbacks in the Earth system, but there are some that are very prominent. Of course, carbon cycle feedback is one, and it works in a funny way that on very long geologic time scales it can be stabilizing, but on the glacial interglacial time scale, as we saw, it was a positive feedback and destabilizing. So I think you already have what I mean by stabilizing and destabilizing. You can think of a thermostat which you set for heating or cooling, and if the temperature, let's say you set it to cool at 72 degrees Fahrenheit, if it gets warmer in the room, the AC will kick in and temperatures will go down. If it gets colder, AC will go off and temperature will remain at 72 or start warming again. So these are called negative feedback loops, which are stabilizing because the thermostat sets the temperature at 72 by adjusting the AC on and off. But there can be positive feedback, as we have already seen, with the temperature increasing, CO2 increasing during the deglaciation. CO2, of course, increasing means it'll warm the temperatures further melt the glaciers, whereas if it's glaciation time, then temperature is cooling, CO2 is dropping, so CO2 dropping further cools the temperatures and favors glaciation to continue. Okay, so we'll look at some examples like this. Let's say we have solar energy coming in, incoming solar energy is going into radiative balance that we already looked at, short wave and long wave, and then there is the term called climate sensitivity, which determines how much energy is retained. Right now the climate sensitivity is defined formally as the warming we will get if we double the CO2 and keep it there till equilibrium. Here climate sensitivity just means what is the net albedo and other things in the system that determine with the incoming solar energy how much is going to go back and what the resultant temperature will be, and associated with that there will be vegetation, precipitation distribution and glaciers and so on, right? So this is a positive feedback in the sense if solar constant increases, incoming solar radiation increases, there is a net increase in energy or net radiative forcing, so energy retained should go up, and if climate sensitivity is positive, for example, and temperature would go up, and that would then increase the outgoing long wave infrared radiation because the thermal energy would go up, which would be a negative feedback. So the way you compute the feedback of the loop is to multiply all the feedbacks within the loop. So 3 positives and a negative makes it net negative. So this would be a stabilizing feedback in the sense when there is an external perturbation to the radiative forcing, the system has an inbuilt Stefan Boltzmann radiative cooling blackbody radiation which would stabilize the temperature. Of course, with human activities and global warming, the question is how fast does this move? Obviously not fast enough because we are increasing CO2 at a fast rates like this, greenhouse gases in the atmosphere. So burning fossil fuels is increasing greenhouse gases, so that's a positive, and that is going to reduce the outgoing long wave because it's trapping outgoing long wave. That's what greenhouse gases do. So that's a negative feedback. So increased greenhouse gases, reduced infrared radiation, and that would lead to warming of the temperature because it has a negative radiative balance, leading to more energy being retained, more temperature. So these two will now go together, but burning fossil fuels can also increase aerosols and scatter sunlight and reduce incoming solar radiation and lead to negative feedback, as we saw. So obviously that this means that in the real world you can have complicated network of feedback, so the net feedback of the entire system is not very easy to determine. It may depend on time scales, so this works at a very different time scales, this works at some radiation time scales, this works at a different time scale, and so on and so forth. So let's look at another feedback. We are looking at ice. So let's say incoming solar radiation again increases, we get net radiative forcing, energy retained goes up, temperature goes up, but that's going to reduce the ice cover, so that's a negative feedback. Reduced ice cover is going to increase the is going to reduce the albedo as well, so they go in the same direction, so that's a positive feedback. That's reduced albedo is going to absorb more energy, so that's going to be a negative. So every time you reduce one, other one increases, it's a negative feedback. If they go in the same direction, it's a positive feedback, of course. So that would then alter the radiative balance again, so you would continue to warm. So this is a very strong positive feedback, and you can see that's because you have even number of negative feedbacks in the system, so the whole system is a positive feedback. And this works in both directions, as we saw before, that as glaciers are building, temperatures are cooling, it may be kicked off by the orbital forcing, but as glaciers build, albedo increases, more energy loss, more cooling, more glacier buildup. Of course, it begins to slow down because as temperatures cool down, atmosphere's ability to hold water vapor goes down. So snowfall rates which are needed to build the glaciers goes down. So the cooling and glacier buildup goes very slow and can take 100,000 years, whereas the other direction where you orbital forcing begins to melt the glaciers, albedo increases, more energy is trapped, more glaciers melt, and more albedo increase. So this can go very fast. Okay, so that's what you have to remember. Both are positive feedbacks, but one is slower and slower, the other one is faster. So abrupt change can happen during deglaciation, and of course we have to worry now because we are warming the climate and melting glaciers, and this can lead to abrupt changes, which is what we are always worried about. Coming back to putting these together, then you can see that you can start here with solar constant changing radiative balance and the outgoing long wave feedback that we looked at depending on the climate sensitivity, and we are adding now here permafrost. So as temperatures increase, permafrost can begin to thaw, which can increase the greenhouse gases in the atmosphere, which can increase the outgoing long wave radiation, but again it's a question of time scales here as well. And there are some complications because it turns out thawing permafrost can create ponds of water which you think would reduce albedo, but also they are beginning to have phytoplankton growing in them and absorbing some of the carbon, so obviously there can be additional feedbacks there. So you can still add the fossil fuel burning on top of that, so you have now solar constant and permafrost feedbacks acting together, and aerosols being part of that as well. So you can begin to see how complicated things get. Now you add another one, or put these three together now, so you have ice albedo feedback, outgoing long wave radiation, black body radiation feedback, and you can have permafrost feedback as well added, so you can combine any number of feedbacks in this sense. You can add carbon feedback here. We already looked at this part. Let's look here. As greenhouse gases increase in the atmosphere, carbon cycle can accelerate and saturate the carbon sinks. For example, ocean sources and sinks are being looked at closely to see if ocean's ability to take up carbon dioxide is being reduced. Or you can have vegetation feedback where there is some evidence of accelerated photosynthesis, because as CO2 increases, the stomata need not open for longer times like before, because higher CO2 can be captured quickly and they can then photosynthesize. So the carbon fertilization effect is present already, is seen in many places, so that can have a negative feedback as well. So just to give you an idea that feedbacks are many in the system, and it isn't always clear what is a net feedback of the system. For example, clouds remain tremendously problematic in terms of inferring their net effect on energy balance with increased greenhouse gases, because if you increase high clouds, you may be net warming. If you increase deep clouds, you may be net cooling. Aerosols may be changing optical properties, and so on and so forth. So now you throw them all together and you can see that you have the blackbody radiation feedback, ice albedo feedback, permafrost feedback, and carbon cycle feedback. So we will see how these things are put together in the climate system and how the models are built, because when you build a model, you're just going to give it energy coming from the sun, and you represent atmosphere, ocean, land, vegetation, as many details as you can, and then you see what the system does. You don't have to put in these feedbacks explicitly. The model should be able to actively represent the feedbacks and produce what are called emergent solutions, things that you didn't expect necessarily from a linear thinking, that these multiple feedbacks together may produce warming that's much more accelerated than you imagined, or climate sensitivity that is reduced because of the positive and negative feedbacks, and so on and so forth. So it gets very quickly very complicated, and models are obviously not perfect, but we will see how the models try to represent the Earth system and how they try to do the feedbacks. And then of course the question is, can we use these models to do past simulations of human migrations? We already mentioned Axel Timmermann's simulations to infer migrations. We'll look at the one simulation here from the University of Victoria Earth System model that we already mentioned, and we will briefly look at the class of models that are used in the IPCC projections for the future, and so on. Okay, so just remember, feedbacks are very important and can be very complicated. We haven't even mentioned all the feedbacks yet. We will mention some more as we look at the structure of the Earth system in terms of its components and the models. Okay.